2.1 and 2.2 Lesson 3, Numerical, Graphical, and Algebraic Approaches to the Definition of Limit. So in Lessons 1 and 2, we looked at, in Lesson 1, we tried to develop a conceptual understanding of what a limit is and what it is not. And in Lesson 2 yesterday, we looked at a couple of instances where a limit may fail to exist, and we looked at a couple of problems that prepared us for today's lesson. So today we want to look at the mathematically precise definition of the limit of f of x as x approaches c is equal to L. And you will be able to algebraically calculate a positive value for delta, which is from the limit definition. And we also saw delta yesterday when we did our problems for any value of epsilon that's positive. And that's also from the limit definition. And we started looking at problems yesterday that had epsilon and delta to prepare us for what we're going to do today, which is to look at the mathematically precise definition of the limit of f of x as x approaches c is equal to L. So here is the definition of limit as stated in your textbook. And we have here, again, this is the notation for limit. The limit of f of x as x approaches c is equal to L if and only if. So what does this mean? And how can we state it in a mathematically precise way? Here's what we're doing. So this is the mathematically precise definition of limit. So what does this mean? It means if and only if for any epsilon greater than 0, no matter how small epsilon may be. So epsilon could be, as we saw yesterday, we had 0.5 for our two examples, but it could be something smaller than that. Epsilon could be maybe 1/10, or even something smaller. Epsilon could be 100th, or even something smaller, 1,000th, or even something ridiculously small. No matter how small epsilon is, let's see if we can continue reading the definition. So the limit of f of x as x approaches c is equal to L if and only if for any epsilon greater than 0, no matter how small, or even something smaller than that. You can always find a delta value greater than 0 such that if the input values for the function are within delta units of c, but not equal to c, then the output values will be within epsilon units of L. This is a mathematically precise way of stating the conceptual understanding that we developed in Lesson 1. So in Lesson 1, this was the conceptual understanding that we developed for what a limit is. As the input values for the function get closer and closer to 1, the output values get closer and closer to what the limit is. That was, and we read this notation, the limit of f of x as x approaches 1 would be equal to L. And more generally, you can have x approaching some value c. And the limit would be whatever it is, signified here by L. And the conceptual understanding we developed on Monday for Lesson 1 is, again, the idea that if you make the input values for f get closer and closer to c, we used a particular example in Lesson 1, but generally c. If you make the input values for the function get closer and closer to c, you will be able to make the output values get closer and closer to whatever the limit is. And we state that conceptual understanding in a mathematically precise way in this definition of limit. So let's see how that's accomplished. So we're saying, what does this mean? It means for any epsilon greater than 0, no matter how small, you will be able to make the output values of the function f be within epsilon units of the limit. In other words, you can make the output values be as close as you would like to the limit just by making sure that the input values are close enough to C. Okay, so if you are able to, for any epsilon greater than 0, you're able to find a delta value greater than 0, such that if the input values are within delta units of C, but not equal to C, then the output values will be within epsilon units of L. And again, going back to the conceptual understanding that we had in lesson 1, the idea that if x is within delta units of C but not equal to C, that is the precise mathematical formulation of the idea that the input values of the function are getting closer and closer to C. Why do we need that not equal to C? Because as we saw in lesson 1, you could have the function be undefined at x is equal to C, but the limit could still exist. So that's why we have that x not equal to C. It really doesn't matter what's happening at x is equal to C, because the idea of a limit is what's happening as x is approaching C. And that is why you have this x not equal to C part, because it could be the case that the function is not defined at C, or it could be defined, but the value of the function at C could be different from the limit. So what's happening at x is equal to C does not matter, and that's what's stated there. And of course, we developed a conceptual understanding of that in lesson 1. Before we go on to objective 2 and algebraically calculating a positive value of delta from this limit definition for any value of epsilon, we want to go ahead and try to understand this mathematically precise definition of limit by looking at a couple of specific values for epsilon. This says for any epsilon, but let's try to make this a little bit more concrete by looking at specific values of epsilon and see what this is stating. So yesterday we looked at number 20, and our function for number 20 is f of x is equal to x minus 2 cubed plus 3, and we found the limit of the function f of x as x approached 2. And you can see from the graph that the limit of f of x as x approaches 2 would be equal to 3. And yesterday we worked with epsilon and delta, and we said if we make epsilon 0.5, we're looking at output values for the function that are within a half unit of the limit, within 5/10 of 3. So we have the line y is equal to 3 plus epsilon and y is equal to 3 minus epsilon. And here are the two lines. So we were thinking about how close the x values would have to be to 2 or C so that the y values, or the output values from the function, will be within a half unit of the limit. And we were able to find that by using a graph. And as you can see from the intersection of the graph of f of x and the horizontal line y is equal to 3.5, you have the point x is equal to 2.79, and the intersection of the graph of f of x and the horizontal line y is equal to 2.5, you have this point with an x coordinate of about 1.21. So if x values are within 0.79 units of 2, then the y values will be within a half unit of the limit. So the delta value was found to be about 0.79. So whenever you have input values for the function that were within 79/100 of C, the output values for the function will be within 5/10 of the limit. So what is the mathematically precise definition of limit stating? It's stating that the limit of f of x as x approaches C is equal to L if and only if for any epsilon greater than 0, no matter how small. In other words, I could make the epsilon value from number 20 yesterday like 0.25 or 0.2 or 0.15 or even something really small like a millionth or a billionth or a trillionth. no matter how small, I will always be able to find a delta value such that when x is within delta units of c, but not equal to c, I will be sure that the output values from the function will be within whatever epsilon is of the limit, no matter how small. So let me demonstrate with a couple of examples for epsilon that are smaller than 0.5. So what if I were to change the value for epsilon from 0.5 to 0.25? What would happen? Well, you would have the limit, which is still 3, plus epsilon, and the limit minus epsilon. So I will have y is equal to 3.25 and y is equal to 2.75. And this is the horizontal line, y is equal to 3.25, and here's the horizontal line, y is equal to 2.75, because the definition of limit says this would be true if and only if for any epsilon greater than 0, no matter how small. I must be able to find a delta value that's positive such that for x values that are within delta units of c, in our case 2, but not equal to c, then I will know for sure that the output values from the function will be within whatever epsilon is of L, no matter how small. So for this particular value of epsilon, can I find a delta value? Yes. Let's go ahead and look at that. So you can see that when I look at the coordinates of the points of intersection between the graph of f and the horizontal line y is equal to 3.25, the x-coordinate of that point of intersection is 2.63. And when I look at the intersection of the graph of f with the horizontal line y is equal to 2.75, the x-coordinate of that point of intersection is 1.37. So c in my example here is 2. So if I have x values that are within 0.63 units from 2, again, how do I get 2.63? It's 2 plus delta, 2 plus 0.63, or you can do 2 minus 0.63 to get 1.37. So when you have input values that are within 63 hundredths of 2, then I know that I will have output values that are within 25 hundredths of the limit. And notice that because I made epsilon smaller, delta also became smaller. When epsilon was 0.5, delta was 0.79. When epsilon is 0.25, delta is smaller now. And again, you want to understand what the definition of limit is stating. It's stating that this is the limit if and only if for any epsilon greater than 0. No matter how small you make it, you can make it much smaller than 0.25. It doesn't matter. As long as you will always be able to find a delta greater than 0, such that if the input values for the function are within delta units of c, but not equal to c, then the output values of the function will be within epsilon units of L. So this definition of limit basically says, let's keep playing this game. No matter how small you make epsilon, if you can always find delta that would satisfy that the output values of the function will be within epsilon units of the limit, as long as the input values are within delta units of c, no matter how small you make epsilon, if you're always able to find delta, that means the limit exists. So let's look at maybe like 2 more values of epsilon that are smaller than 0.25 before we try to generalize from this and go on to objective 2, where you will be able to algebraically calculate a positive value for delta from this limit definition for any epsilon greater than 0. So we're doing it graphically for certain values of epsilon, like 0.5 and 0.25, but if we can show algebraically that for any epsilon greater than 0, we can always find a positive value for delta, so that if input values are within delta units of c, the output values of the function will be within epsilon units of the limit. Then by this definition, the limit exists. And right now we're just looking at specific values of epsilon and finding specific values of delta, and then we want to generalize for any epsilon, no matter how small. Whether it's a millionth, a billionth, a trillionth, if I can find a delta value, so that whenever the input values are within delta units of c, the output values will be within epsilon units of L, no matter how small epsilon is, then by this definition, I know the limit exists. So now to get you to see this idea, I'm going to change my epsilon value to something even smaller than 0.25. I'll make it 0.15. So if epsilon is 0.15, the range for the output values that I'm considering would be the limit plus epsilon and the limit minus epsilon. So it would be 3 plus epsilon, which would give me 3.15, and 3 minus epsilon, which would give me 2.85. So here are the horizontal lines. Y is equal to 3.15, and y is equal to 2.85. So again, looking at the definition of limit, what does this mean? It means for any epsilon greater than 0, no matter how small. We've looked at two values of epsilon already. Here's a third one. But really, you need to be able to do this for any epsilon, no matter how small. It could be 1 billionth, a trillionth, a quadrillionth. No matter how small epsilon is, you must always be able to find a delta value greater than 0, such that if the input values of the function are within delta units of c, but not equal to c, you will know for sure that the output values of the function will be within epsilon units of L, no matter how small epsilon is. And we're going to look at how we can show that algebraically, how we can show this would be true for our particular limit here algebraically. We're going to look at that next. And we're working towards the generalization by looking at specific values of epsilon. So if epsilon is 0.15, if I want the output values of the function to be within 1500ths of the limit, how close must the input values be to 2, which is, of course, our c value? And to answer that question, we'll look at the coordinates of these 2 points of intersection. The intersection of the graph of f with the horizontal line y is equal to L plus epsilon, and with the horizontal line y is equal to L minus epsilon. So here is what we see. So we have the x-coordinate of this point of intersection is 2.531. The y-coordinate is 3.15. And here, the x-coordinate of this point of intersection is 1.469. The y-coordinate is 2.85. So what that means is, when epsilon is 0.15, how small would delta have to be? It would have to be about 0.53. So if epsilon is smaller, delta will have to be smaller. And look at, once again, the definition of limit. This limit, what does that mean? It means for any epsilon greater than 0, no matter how small, whether it's 5/10ths, 2500ths, 1500ths, or even something really small like a billionth, you must be able to find a value for delta greater than 0 such that whenever the input values are within delta units of c, in our particular example c is equal to 2, but the input values are not equal to c, then f of x will be within epsilon units of L. In other words, this is a precise way of stating that you can make the output values of the function arbitrarily close to the limit by making sure that you take input values that are close enough to c. but this is a mathematically precise way of stating that we can work with to do the next part of what we want to accomplish. As we prepare to look at objective 2, which is to algebraically calculate a positive value for delta from this limit definition for any epsilon greater than 0, so that we will know that for any epsilon greater than 0, no matter how small you want to make it, we will be able to show algebraically that there is a value of delta that you can find greater than 0, such that if x is within delta units of c but not equal to c, then y will be within epsilon units of L. So we want to show, using this mathematically precise definition of limit, that in fact this limit is true. And that's called an analytical approach because we're using this definition. We looked at it numerically and graphically in lesson 1, and now we're going to look at it algebraically by using this definition of limit. And of course, the title of this section is Numerical, Graphical, and Algebraic Approaches to the Definition of Limit. And to get ready for that, make note of one thing. So if you look over here, what's special about this point? Well, look at the coordinates. The y-coordinate is, generally speaking, it's going to be the limit plus epsilon. Epsilon was 0.15. The limit was equal to 3. And here, 3.15 is 3 plus 0.15. So it's the limit plus epsilon. And what's special about the x-coordinate here? It's c, which of course was 2, plus delta, which was about 0.53. So here you have c plus delta. And if you look at the other point of intersection between the graph of f and the horizontal line, y is equal to the limit minus epsilon, 3 minus 0.15, giving us 2.85. If you want to generalize the coordinates here, you're going to have, for the y-coordinate, the limit minus epsilon. And for the x-coordinate, if you look at the x-coordinate here, what is the x-coordinate? 1.469, which would be c, which is 2 in our particular example, minus delta. Delta is about 0.53. So we have c minus delta. So that's something important for you to understand as we now look at objective 2. So students, now we take a look at objective 2 for number 20 that we were just looking at. And we spent a great deal of time investing in knowing and understanding the mathematically precise definition of the limit of f of x as x approaches c is equal to L. And now we're going to work with that to do objective 2. We will be able to use the mathematically precise definition of limit to algebraically calculate a positive value for delta from the limit definition for any value of epsilon. So in the lead up to what we're about to do now, we looked at number 20 with 3 different values of epsilon. And for each value of epsilon, 0.5, 0.25, and 0.15, we were able to find corresponding values of delta. 0.79, 0.63, and the last one I forget, but I think it was something like 0.53. So now we want to just do this generally for any epsilon greater than 0, even something like a billionth, a trillionth, whatever. I want to show algebraically, using the definition of limit, that I will be able to find a value for delta, so that whenever the input values for the function are within delta units of c, but not equal to c, then the output values of the function will be within epsilon units of L, no matter how small epsilon is. And that is what the mathematically precise definition of limit is stating. It is just a mathematically precise formulation of the conceptual understanding that we developed in lesson 1, which states that you can make f of x closer and closer to the limit by taking the input values closer and closer to c. But now we make those words closer and closer more precise by using epsilon and delta. So here's our first example for objective 2. You'll be able to algebraically calculate a positive value for delta from the limit definition for any value of epsilon greater than 0, no matter how small. And the instructions are calculate algebraically a positive value of delta for any epsilon greater than 0, no matter how small. Our function for number 20 is f of x is equal to x minus 2 squared plus 3, and we want to take the limit of the function as x approaches 2. So 2 is, of course, the c from the limit definition, and the limit of this function as x approaches 2 is equal to 3. We believe that to be the case by looking at the graph, and it's a reasonable belief to have, but now we're going to prove that this is in fact the case. How do we prove that this is in fact the case? By using the definition of limit. So when we looked at the graph, it was, we didn't see it like this, but it was like our belief from the graph that the limit was equal to 3. But now we're going to be able to prove analytically by using this definition of what a limit is that this is in fact true. And how do we do that? Exactly doing what the instructions state, by calculating algebraically a positive value of delta for any epsilon greater than 0, no matter how small, because the definition of limit states if the limit of f of x as x approaches c is equal to L, what does that mean? It means for any epsilon greater than 0, no matter how small, you will be able to find a delta greater than 0 such that if the input values for the function are within delta units of c but not equal to c, then the output values will be within epsilon units of L. In other words, you can make the output values of the function as close as you would like to the limit by making sure that you take the input values close enough to c. So looking at the graph here, as we stated at the end of our previous example, here you have a point here, and it would have coordinates. For the y coordinate, it would be the limit plus epsilon, and for the x coordinate, it would be c plus delta. And here you have a point whose coordinates would be the limit minus epsilon for the y coordinate, and you have c minus delta. So how are we going to do 220D? Calculate algebraically a positive value of delta for any epsilon greater than 0, no matter how small. Here's how we're going to do it. F of x is the y coordinate. It's the output. And you're basically going to replace x and y with the coordinates of one of these 2 points. You're going to replace x and y with the coordinates of one of these 2 points. Which one of them should you use? You should use the one that's closer to the point on the graph at which you have the limit. So we're taking the limit of the function as x approaches 2, and we're saying that the limit of that function as x approaches 2 is equal to 3. So this is the point that we want to sort of be our reference point as we think about which of these 2 coordinates we should use. We should use the coordinate of these 2 that's closer to whatever the limit, to whatever c is, not the limit, but to whatever c is. And what is c in our problem? C is 2. So we need to use one of these 2 points. Which one do we use? The one that's closer to c. Not the limit, but the one that's closer to c. And c is 2 in our problem, which is right here. Which one of these 2 is closer to c? This graph actually has symmetry, so you can use either one. But sometimes you won't have symmetry. And if that's the case, you have to choose the coordinates of the point that is closer to, not the limit, but to c. Okay, and in this problem, c is 2. And again, here it doesn't matter because these are both equally close to c. And why do you want to choose the point that's closer to c? Because you want to make sure that once you've found your value for delta, whether you are c plus delta or c minus delta, in that range, if the input values are in that range, you want to make sure that the output values will be within epsilon units of the limit. So I will just go ahead and use this particular point for our current example. And basically, I want to take that, substitute for x and y, and then solve for delta in terms of epsilon, so that I will be able to show that no matter what epsilon is, I will be able to find a value for delta. So I begin by making the substitution 3 plus epsilon for y and 2 plus delta for x. And now I just want to solve for delta in terms of epsilon. So how do I do that? Well, you can start here inside the parentheses and you can simplify, because 2 minus 2 will be 0. So that leaves you with 3 plus epsilon is equal to delta cubed plus 3. And then you can subtract 3 from each side of the equation. So then you're just left with epsilon is equal to delta cubed. And now you can easily solve for delta by taking the cube root of epsilon. So basically, that's it. What have we shown? We've shown that whatever you give me for epsilon, all I have to do is take the cube root of that, and I'd be able to get a value for delta. And you can make epsilon astronomically small if you want. I will just take the cube root of that and tell you if x is within delta units of, in this case, 2, then y will be within whatever you gave me for epsilon of the limit. And you can try it for epsilon is equal to 0.5. Substitute 0.5 here, and you will get that delta is 0.79, as we saw earlier. And if you substitute 0.25 for epsilon in that formula, you'll get that delta is 0.63. By, of course, taking the cube root of 0.25, you would get 0.63 for delta. And if you substitute 0.15 for epsilon, you will get 0.53 for delta. But now, you're not restricted to just these three values of epsilon. You can make epsilon whatever you want it to be. You can make it as small as you'd like. So we have shown by the definition of limit that the limit that we have here, the limit of f of x as x approaches 2 is equal to 3 is in fact the case by using this mathematically precise definition. You can make epsilon as small as you would like for any epsilon greater than 0, no matter how small you choose epsilon to be. You will be able to find a value for delta by using this equation. Delta is equal to the cube root of epsilon, such that if x is within delta units of c, which in our problem is 2, but not equal to c, then y will be within epsilon units of L. And of course, we have 3 specific values of epsilon and 3 corresponding values of delta that you can get from this equation that we had also gotten from our prior work. So let's take a look at a second example here. Show algebraically that there is a positive value of delta for any epsilon greater than 0, no matter how small epsilon is. So we have f of x is equal to 0.2 times 2 to the x, which is a transformation of an exponential function. And when we take the limit of this function as x approaches 3, if you look at the graph, here's x is equal to 3. And from the graph, you can see that the y values are approaching 1.6. So the limit graphically can be determined to be 1.6, but it's sort of like what you believe it to be until you prove it using the definition of limit and the algebraic approach that you saw in the previous example. You can also approach this limit numerically, as you see here. As the input values get closer and closer to 3, the output values appear to be getting closer and closer to 1.6. But now we want to prove this by using the definition of limit, which means we have to show that for any epsilon greater than 0, no matter how small, I will be able to find a positive value of delta such that if the input values are within delta units of C, which in our problem is 3, but not equal to C, then the output values will be within epsilon units of L, which in our problem is 1.6. So one thing to note here is, here we have C, which is 3, and we have a couple of points that we want to look at. To the right of 3, we have this intersection between the graph of the function f and the horizontal line y is equal to L plus epsilon for some epsilon. And then to the left of C, we have this point of intersection between the graph of f and the horizontal line y is equal to L minus epsilon, whatever epsilon may be. But one thing that you might notice is this graph is different from what we looked at in our first example. We don't really have symmetry about x is equal to 3. In fact, this point here would have coordinates L plus epsilon for y and C plus delta for x. And the point down here will have coordinates L minus epsilon for y and C minus delta for x. And of course you can replace L with 1.6 because the limit in this problem is 1.6. And you can replace C with 3 because C is equal to 3 in this problem. But the question then becomes, which of these 2 points should you choose? You should choose the one that is closer to C. And because of the way the graph of f is, the point on the right is actually closer to C than the point on the left. And so you want to use this set of coordinates when you're substituting for x and y in this equation to solve for delta in terms of epsilon. Why is it that you don't want to choose this point? Because this point is further from C than the other point. So if you solve for delta using these coordinates, you'll get a value for delta, but you will not guarantee that if the input values are within delta units of 3, the output values will be within epsilon units of 1.6. Why not? So to understand why, you need to use the point L plus epsilon and C plus delta rather than L minus epsilon and C minus delta. Consider this particular value of epsilon, where epsilon is equal to 0.5. So you have L, which is of course 1.6, and C, which is 3. And I'm choosing epsilon to be 0.5 in this particular example. So we have 1.6 minus 0.5 here. And then for C, we're going to have 3 minus delta here. You can see that when epsilon is 0.5, if you work with the point on the right, you get a value of delta that is 0.392. And if you work with the point on the left of C, you get a different value for delta. Delta would be about 0.55. So the problem with choosing the left point to find delta is you'll find a value of delta and you would not meet the requirements from the definition of limit, because if you're saying as long as input values are within 0.55 units of 3, the output values will be within 0.5 units of 1.6. That would only be true to the left of 3, but not to the right of 3. Because if you add 0.55 to 3, then you will get 3.55. And where is the vertical line 3.55? I'm going to show you using gold. It would be about over here. And you can see that there will be some x values that are within (3 minus 0.55) and 3 plus 0.55, but you run into problems over here because if you look at the graph, there are going to be some points on the graph in the portion that I'm shading in green here that are going to be above the horizontal line y is equal to 2.1. So that's why you don't want to choose the left intersection point between the horizontal line and the graph, but you want to choose the right point because it's going to give you a smaller range of input values which will work on both sides rather than just one. So now we're going to replace f of x with 1.6 plus epsilon, and we're going to replace x with 3 plus delta and solve for delta in terms of epsilon, just like we did for the previous example. F of x again is y. So having made the substitutions for x and y, as we just discussed, now we're ready to go ahead and solve this equation for delta in terms of epsilon. And in doing so, we will prove analytically that the limit of the function as x approaches 3 is, in fact, 1.6 by this definition, by showing that for any epsilon greater than 0, no matter how small, I will always be able to find a delta greater than 0, such that if the input values are within delta units of c, in our case 3, but not equal to 3, then the output values will be within epsilon units of L, which in our case is 1.6, no matter how small epsilon is. So you can make the output values as close as you'd like to 1.6 by making the input values close enough to 3. So you just need to solve for delta in terms of epsilon here, and the way you can do that here is first you can write 2/10 as 1/5. 1 divided by 5 is 2/10, and then you can multiply both sides of this equation by 5. So when you do 1.6 times 5, you will get 8. So when you're multiplying the left side of the equation by 5, you distribute 5 to 1.6, you get 8, and then you get 5 times epsilon. On the right side, 5 times 1/5 is 1, so you're just left with 2 to the 3 plus delta power. So now you need to try to solve for delta, but it's in the exponent here, so you need to undo the exponentiation by taking a logarithm. So you can either do log base 2, or you can do a logarithm of a different base, such as base 10. It really doesn't matter. So you have log base 2, log base 10 of 2 to the 3 plus delta. There is a property of logarithms that says you can take this and bring it to the front. If you have log base a of x to the n, you can write that as n times log base a of x. And that's what we're doing here. So now we have logarithm, log base 10 of 8 plus 5 times epsilon is equal to 3 plus delta times the common logarithm of 2. So what is the next step that we want to take to solve for delta? We will now divide both sides of the equation by log base 2. So now we have, on the right side, we will just have 3 plus delta, and on the left side of the equation, and we can switch the two sides, we will have log base 8 of 5 plus epsilon, log base 10, the common logarithm of 8 plus 5 times epsilon, divided by the common logarithm of 2. The common logarithm of 2. And then to solve for delta, just subtract 3 from each side of the equation. And there you have it. So whatever epsilon we consider, no matter how small, I will be able to find a value for delta using this formula, showing that by definition, the limit of the function as x approaches 3 is 1.6. Epsilon is positive and delta will be positive. You can do some analysis of this equation to understand that this particular term will be greater than 3, so when you subtract 3 from that, you'll get a positive value for delta. So this is showing, using the definition of limit, that the limit of this function as x approaches 3 is, in fact, 1.6. So today we looked at these two objectives. You will know the mathematically precise definition of the limit of f of x as x approaches c is equal to L, and you will be able to algebraically calculate a positive value of delta from the limit definition for any epsilon greater than 0, as we saw in our last two examples.